1 Charged Tapes for Physics 2. For this lab, we utilized at-home materials to observe the behavior of electric fields and charges as they interact with each other. The objectives were to observe these interactions and use them to estimate values such as gravitational force and electric charge on the floating tape. We're able to calculate these values using physics principles from which we learned in class. The concept of Newton's second law helped us to understand the force of gravity acting on the tape, as we know the acceleration of an object is directly proportional to the net force and inversely proportional to its mass. We also utilized Coulomb's law, which quantitatively states that the closer charges are to each other, the stronger the interaction between the two. For this lab, we treated each tape as a point charge and that each tape were of equal magnitude of charge. We also treated air resistance as negligible and ignored it in our calculations. We charged pieces of clear tape so that they would exhibit behaviors of point charges. To do so, I stuck a tape on my desk and then stuck another piece of tape of equal length on top of the first. Then in one motion, I removed the second piece from the first, and this resulted in a charged piece of tape. I then set up the pieces in a diagram as pictured and measured the distance and took until the tapes began to float, repelling one another. I recorded my observations as shown, calculated the mass of my tape where 1 gram equals 1 meter of clear tape. I also noted the distance between the two to be 0.021 meters when they began to repel each other. Using these values, I calculated the gravitational weight of the tape, which portrayed the force on the tape in the negative y direction due to gravity. I also calculated the surface area of the tape using the formula length times width. This value will be used to calculate the number of atoms on the surface of the upper tape, which I calculated by dividing the surface area of the tape by the area of an atom, a standard value of 1 times 10 to the negative 20. This yielded a value of 4.6 times 10 to the 17 atoms. First, I calculated the force of gravity on the tape using Newton's second law. Because we know net force equals force of gravity and electric force, we can assume that when net force is 0, the electric force is the reciprocal of the gravitational force. Furthermore, I calculated the charge of the tape using Coulomb's law. I rearranged the formula to solve for Q, which we assumed to be equal for each piece of tape earlier. Using the Coulomb's constant K, the magnitude of the electric force that I calculated before, and the distance between the two pieces of tape when they began to repel, I calculated the charge of the tape to be equal to negative 9.8 times 10 to the negative 9 coulombs. I then calculated the number of excess electrons on the tape by dividing the tape by the charge of an electron. Since they are the same sign, I ignored charges. Using this value, I found the ratio of deficient electrons to atoms on the tape to be 1 electron per 7.4 times 10 to the 6 atoms. Next, I created the computational model on GlowScript to model the behavior of the tapes as point charges as they interact with each other. I started by coding in the known and recorded values we discussed earlier, such as Coulomb's constant, the charge of a proton, and the physical property values of the tape. I then coded in the laws to calculate gravitational force, electric force, and the electric field of the tapes. After running the program, we observed the upward and downward forces acting on the floated tape with the yellow and green arrows. The code generated the downward gravitational force with the green arrow and the upward electrical force of the yellow arrow, and calculated the value of each. We noticed they are equal to our estimates as they are both 1.99 times 10 to the negative 3 newtons. The code also calculated the charge of the tape as negative 9.87 times 10 to the negative 9 coulombs, like we calculated. In conclusion, our computational model proves to be accurate depiction of the interactions between the two charged pieces of tape, and the values calculated using Coulomb's law and Newton's second law. After this procedure, we can expand our understanding by considering alternate scenarios. We're asked the question if electrons had positive charge and protons had negative charge in the case of the charged tape. If this were the case, we would first note that the tapes of the same charge, whether they be negative or positive, would still repel each other as like charges do. If only the charges on the tape changed and the surroundings remained the same, then we would see that the scenario where tape previously repelled objects, it would attract, and vice versa, because the inverse charges would interact differently. However, if all charges were flipped, we would see the same interactions between charged objects, because the law of like charges repelling and different charges attracting would remain the same. It's important to handle the charged tape as little as possible because the hands of our bodies act as conductors. Therefore, the electrons on the surface of the tape are attracted and able to move freely into the surface of our hands as they act as a conductor. Therefore, the more that we handle the tape as it was charged, the more electrons are transferred to our hands, and therefore the magnitude of the charge in the tape would decrease, and the interaction with the surroundings of the tape would become less strong.